Welcome, everyone.
All right. Thank you so much for joining us today. My name is Judith Wright. I'm the Assistant Director at the Homewood Public Library. I'm really excited to introduce Carol Holmberg. She is a NASA Solar System Ambassador and Planetarium Manager at the Museum of York County in Rock Hill, South Carolina. She spoke with us earlier this year about the Mars Perseverance mission, and so I'm excited to welcome her back to talk about the Webb telescope. And Carol, I'm going to turn it over to you, but I am recording this session, and afterwards I will send out the Zoom YouTube link to everyone so you can share it with your friends or rewatch it and get more information.
Okay, and then embarrassingly right now, I can't find my mouse and I want to resume the slideshow. So let me see if this will work. No.
Oh, good.
Okay, everything worked out well in practice. I might have to, oh, there's my mouse at the very top. Okay. And of course you're recording this.
It's
so
okay.
It would fail.
We've so one technical difficulty we had during a Zoom program was when the power went out. And that was fantastic. Like they were recording here at the library and our power just went out. So
well, let me stop screen sharing, stop share, and see if that will fix it. Yeah, I once was in the middle of an outpatient operation and the power went out. That was pretty scary. Okay, so we want to start sharing again. Share screen, and let's go for my PowerPoint slide. Share. Well, there it is in PowerPointed. My name is Carol Holmberg. My day job is the planetary manager in South Carolina, near Charlotte, North Carolina, but I am also a volunteer JPL NASA Solar System Ambassador. I bet you didn't know there were ambassadors to the solar system. And it's in that capacity that I'm talking to you today. I've been trained on the James Webb telescope. And this talk, the slides do come from the James Webb Community Events team, and also one of the James Webb scientists, Eric Smith. And the talk is going to have 4 parts: how Webb came to be, why study infrared light, which is what the Webb is designed to show. Let's explore the universe with Webb, what it's designed to tell us about the universe, and then all about the telescope itself. Now, how Webb came to be. Right now, this is an illustration, if you can see it, of a planet, an exoplanet, a planet from outside the solar system. 10 years ago, we didn't really know about any planets outside our own 8. There's 8 now. But now we've got hundreds and even thousands, and there should be a whole bunch more. And James Webb, it's named after James Webb. And James Webb was an administrator of NASA. And originally I was like, oh, it's named after an administrator, not a scientist. How boring. But James Webb actually was the one who wanted NASA to have a strong science program and oversaw the Mercury and Gemini missions, and as well as the first missions to the moon, Mariner and Pioneers, the first ones to kind of explore the solar system. So he was an innovator and really focused on science. And so that's why James Webb Space Telescope, which is going to be innovative and focus on science, makes sense to be named after him. And our science explorations have gotten better and better as we look at the universe, culminating with Hubble Space Telescope, which is still in orbit. And Hubble has seen so much, but there's stuff that it can't see. It's just not in the appropriate range. It's not big enough, and technology has changed. So we can think of Webb in some ways as being an extension of Hubble. And this was something Hubble took a picture, except for maybe a dozen foreground stars. Everything you see here is a galaxy. And this is from the Hubble Ultra Deep Field. Hubble spent about a week staring at this seemingly empty place in space and saw thousands of galaxies. And this ultra deep field is like the fourth one that it's done. Everywhere in space Hubble looks, it sees lots and lots of galaxies. And the bigger ones, those are ones that are younger and relatively close. That means the light hasn't taken us a long time, but some of them are billions of years old because there are billions of light years away. And Hubble, try as it might, cannot see the very first galaxies. There's a limit to what Hubble can see. So the James Webb is designed to take us to the early universe. And why study infrared light? Visible is just that little rainbow right there. That's what our eyes can see. But the electromagnetic spectrum encompasses a whole lot more. There's a whole lot more that we call light. Ultraviolet, X-ray, gamma rays as we get to higher energies, and infrared, microwave, and radio as we get to lower energies. And you can see on the bottom, the Hubble Space Telescope is designed for mostly visible light. It sees a little bit in the infrared. We call that the near infrared. The James Webb is designed to see pretty much only the infrared and go all the way from near infrared to mid infrared as well. Now, there have been infrared telescopes in space before. The Spitzer is the one that recently died about 2 years ago, and it looked in the infrared as well. James Webb will see the infrared in a lot more detail, even though it won't go as far into the infrared, as long a wavelength as Spitzer did. And to talk more about infrared, I'm going to start with something that we're kind of familiar with here on Earth, animals. And this is invisible light. And the picture on the left are meerkats, so cute and fuzzy, and everybody loves them. And what's on the right is a freshwater crocodile. And meerkats are warm-blooded and crocodiles are cold-blooded. So when we look at the infrared, what we see is that the meerkats glow brightly because they're warm. And that's what infrared light sees. It sees warmth, it sees temperature. We glow in infrared. Stars glow invisible, but planets will glow in infrared. And so meerkats glow quite brightly. The freshwater crocodile, being more room temperature, it doesn't glow as brightly. It has just come from a warm water pond, and you can see that in its in the lower left of its image. You can see that it's bright. It's the brightest thing in that image, and so the crocodile has left that and still retains a little bit of heat from it, and you can tell that. So there's lots of information that you can tell by using infrared, different information that you can gain from visible. And here is the same thing, except for astronomical things. This is the Eagle Nebula, the pillars of creation, some people call it. And in visible light, you see those beautiful, beautiful pillars. In near infrared light, you can see the hot stars glowing through the seemingly opaque levels of gas. So infrared can peer through and examine through dust. So you can see the stars within and the stars behind. In the right, that's the mid-infrared, and the only telescope that we've been really able to look through, or the best one, I should say, not the only, but the best one has been Spitzer, and you can see that it's kind of blotchy. Webb will see mid-infrared with the same clarity as we can see the near-infrared and visible light through. So it will be a bit of a game changer when we look through dust and see things farther away. And so let's explore the universe with Webb. James Webb has 4 primary goals. The first one is to look at the early universe. The second is to look at galaxies through time, particularly the early galaxies, the first galaxies. The third is the star life cycle, a lot of which is hidden dust and gas in visible light. And the fourth one is to look for exoplanets, other worlds. And usually the planets are not as hot as the stars. The stars glow with visible light, but the exoplanets will glow primarily with infrared light. So they're hoping for all 4 things with Webb. And maybe the most exciting thing are discoveries we can't even think of yet. You know, it's going to look for things that we don't even know about or know to look about. And that is what makes science really exciting. I thought I would start with the early universe, the first goal. And this shows cosmic reionization, which was a little bit confusing to me. I know what reionization means, things that become charged again. But when the universe began in a Big Bang, it was really, really hot. And except for the cosmic background, you couldn't see anything. The light was bouncing back and forth in all of the really compacted material. And as the universe expanded, it was still pretty opaque with all of that light. But eventually it became cool enough that the ions recombined, that atoms formed. And when the atoms reionized again, cosmic reionization, the universe cleared. So after reionization, the universe became clear rather than opaque. And that's where we can see light from. We can't, even with James Webb, we don't think we can go all the way back to the Big Bang because the light wasn't able to escape or record information from then. So we're going to go to the early universe several 100 million years after the Big Bang. And that's what Webb will do for us. And when the stars began forming, and then they assembled into galaxies, and the galaxies became more massive, that's what we're hoping that Webb will see. The early galaxies. We can't see stars before they assembled into galaxies. The universe wasn't clear enough. I should say, we don't think. We haven't seen that far back yet, but Webb hopefully will see as far back as the light will go. And as light travels, it stretches because the universe is expanding. So stuff that might be yellow now, as we look back to a billion years ago, a billion, something that formed a billion years ago, a billion years back in time, it looks red, not yellow, because the light is stretched. And as we look back even farther, instead of visible, that light will be infrared. So we are hoping to look for light from distant galaxies by looking in the infrared. Distant galaxies, the early universe, because something that is 1 billion years, that is 1 billion light years away, we'll see from 1 billion years ago. And something that's 13 billion light years away, we'll see from 13 billion years ago. So if we want to look at stuff that's 13 billion years old, we're going to have to look way, way in the infrared. And we hope to discover some of the very first galaxies. You can see in the little inset, and it looks red. It's blobby and it looks red. It's actually blue, hot stars that were blue when they formed, but because it's coming from so many billions of light years away, they look red. And the infrared, James Webb should show it to us better. And that's what galaxies looked like long, long ago. But still, that is not the first galaxies. Those are relatively young galaxies, but not quite the first. And how are we going to know what the first galaxies look like? We can make a flip book and look from the first galaxies, the farthest little image there, all the way to modern galaxies, and see how galaxies evolve, galaxies over time. And I believe my next image, or my next slide, galaxies over time, is actually a video. So let me see if I can start the video.
Galaxies through time. Telescopes allow us to see very far away, and also to see light that was emitted long ago, which is like looking back in time. By viewing the universe at different distances and eras, we have evidence that galaxies change over time. They grow, collide, and merge with each other, and form new stars. The most distant, earliest galaxies we have seen tend to be smaller and less structured than those in the nearby universe. How did galaxies evolve over billions of years, from the early universe to the era of our own Milky Way? How can we learn about the forces that drive this change? Using images of many different galaxies throughout the history of the universe, astronomers can assemble something like a galactic flipbook. Patterns emerge. Some eras were big from mergers and new star formations, while during others, astronomers see trends for growth in larger galaxies with supermassive black holes at their centers. Together, these images provide an outline of the average galaxy's story. However, the opening chapters are still blank. This is because the universe is expanding, and as space itself stretches, so does the wavelength of the light from the first galaxies, putting them beyond the detection of our most powerful telescopes. The story of the universe and its galaxies is like other stories. If you miss the beginning, you lose a lot of understanding. Seeing the light of the first galaxies provides a more complete picture of galaxy evolution. NASA's James Webb Space Telescope was specially designed to detect the ancient, stretched light from the first galaxies. Webb will fill in the blank pages in the flipbook of galactic history and examine the middle eras in new detail, providing essential insight into some of our biggest questions. How does the universe work? And how did we get here? Galaxies.
Okay, and the other thing about galaxies that I know I want to know is about black holes. What we know is that a lot of galaxies have black holes in their center. Which came first, the black hole and the galaxy and the stars, they were drawn to it, so the galaxy formed around the black hole, or once the galaxy was formed, the black hole came into being. So the black hole or the galaxy, I guess, is a fundamental question that hopefully Webb will find for us when it looks at those early galaxies. Will it see black holes without a galaxy around it, or will it see galaxies without black holes? So I'm hoping that Webb will determine that. And now how stars form, live, and die. The third thing that it wants to see. Well, when stars form, as to the left shows, they form, and this is called the Carina Nebula, and it's informally called Mystic Mountain, which sounds very pretty. Here's Mystic Mountain, because when stars form, they form in these huge layers of gas and dust. You can't see the stars forming within, but through infrared light, a lot of the dust peels away and you can see more. And if you remember that image that I showed earlier that had the Spitzer, the mid-infrared, we can't see right now in mid-infrared that detail, and hopefully we'll be able to see more detailed with Webb and learn how stars form, how they live their lives, and eventually how they die. And in star-forming regions, Webb will detect molecules, and by doing that, it will see what those clouds are made of, and learn a whole bunch more about what stars are made of as well, early stars. So it's really exciting about that. And it is not going to only look at exoplanets, but it's going to re-examine the planets of our solar system, all except Earth, the Moon, Mercury, and Venus, all, and the sun, of course, all too warm, but it can do the outer planets. If it tried to look at Earth or the Moon, its sensors would burn out, fry out. It's too bright for them. So it's going to, this right here is Jupiter. And you can think of the infrared as showing temperature. And in this picture is the great red spot. It's towards the bottom. And maybe you can see that oval circular kind of shape. It's dark. The great red spot is not as hot as a lot of the cloud layers. So it is going to, Webb is going to look at Jupiter and see the temperature of all the different layers. You can see that there's some spots that are warm near the top. There's some blobs near the middle that are kind of glowing. And remember, the brighter it is, the warmer it is. So it can learn a lot about the clouds of Jupiter. The great red spot is actually been called is informally called the great non-blue spot. There's nothing blue about it. It really doesn't have any more red than the rest of Jupiter. It just has less blue. So it looks red in contrast. And you can see also from this that it's not as warm as some of the other parts of Jupiter. And this shows an exoplanet, a planet around another star. Actually, there's 4 planets here. The star has been blocked out by something called a coronagraph. And you can see the little star symbol where the center of that star was. But hopefully around it, you can see 4 planets that are orbiting. This was taken by the Keck telescope in Hawaii over the course of 7 years. So none of them have really made it in 7 years all the way around, but you can see 4 planets on this and 1 solar system. Hopefully Webb will help us discover a whole bunch more in the way of exoplanets. It's been theorized that the number of exoplanets probably about equals the number of stars. Every star should have about 1. Some stars don't have any planets, but a lot of them would have planet systems. And we are just on the cusp of seeing lots of planets, Earth-sized planets around other stars. And that's really exciting. And infrared light will help us see those stars, planets around nearby stars, because remember, the stars glow invisible, but the planets glow in infrared, and planets are very close to their stars. So we need a good instrument to be able to detect them. And let me go to the next one. Okay, here we go. And we can also see the atmosphere of planets, and especially we especially want to look at exoplanets to see what atmosphere they might have. This shows the atmosphere of Earth. Webb is not going to look at Earth, but this is by example. And this shows the light absorbed. So it's kind of reversed. There's less light coming from the highest peaks. And you can see if you look at Earth's atmosphere in the infrared, carbon dioxide and water and methane and even oxygen, a lot of which they say comes from life on Earth, plant life. So you can discover all of those things just by looking at Earth from the infrared, and hopefully we'll be able to look at exoplanets and see what they have. Now about the telescope. James Webb is definitely a feat of engineering. I have these 3 pictures showing Webb in process. The one to the left is they're testing the mirror segments. The man in his hand, you might be able to see a flashlight. He's testing to make sure that all the mirrors are calibrated correctly. And you can see the guy in the cherry picker in the lower right, and the upper right, he's also doing some testing. And these were from 2016 to 2019, these pictures. And Webb, you might have noticed, is got a honeycomb of mirrors. It's much bigger. It's about 3 times wider than the Hubble. Hubble is about 8 feet. The mirror is about 8 feet high, and the Webb mirror is about 24 feet high. So it's going to be bigger, and it's done with segmented mirrors, and that way the mirrors can be folded. Each individual mirror can be folded in, and once Webb is in space, it can deploy it. It's too big to send Webb up on a rocket ship. And here's kind of a comparison of the two. That's Hubble on the left. Hubble on the left, and its mirror is about 8 feet wide. It does visible wavelength pretty much. It operates at about room temperature, and it was launched in 1990, and it's in low Earth orbit, about 400 miles up. It was launched on the Space Shuttle Discovery 28 years ago. Now on the right is Webb. Webb is about 3 times longer, and you can see it's mostly in the infrared, and it's going to operate in very cold temperatures, and it's not going to orbit Earth. It's going to be at Lagrange 2. I'm going to talk about that a little bit later, what that orbit means. And they think it will last 5 to 10 years. They've got everything, they're saying 5 years, and they're hoping for everything to be within 10 years at least. NASA sometimes is much longer than that. The problem with Webb is that it's so far away from Earth, it cannot be serviced, unlike the Hubble. If something goes wrong with Webb, unlike the Hubble, there's no going back. And also, rather than launching on the space shuttle, it's launching on a European Space Agency vehicle, the Ariane 5. And hopefully it will launch in December. Now, a lot of what Webb does, other than in the infrared rather than the visible, so less in the way of pretty pictures, is a lot of it is spectroscopy. It's going to split light. Rather than pictures, it's going to be data and graphs. A little less exciting, more boring, a lot of people would say, but there's a lot of information that you can get with spectroscopy. And Webb has 4 instruments: the near Earth spectrograph, the near infrared spectrograph, the near infrared imager and slitless spectrograph, the near infrared camera, and mid-infrared instrument, near spec, nearest, near cam, and MIRI. These 4 instruments are integrated. All of the instruments in Hubble were separated, so each one could be serviced separately. That's not true with Webb. All of the instruments are together in one area, and each one has redundancy built in because they know it can't be serviced. And this is the integrated science instrument module at the very bottom. It actually shows Webb all folded up and ready to go. The mirror all folded up and ready to go, but all the instruments are integrated into a single module, which will keep them all nice and cool. They'll all be on the cool side, but means that one can't be swapped out the way that they could in Hubble. So where is Hubble's orbit? It is in L2. There are 5 Lagrangian points with relationship to the Earth and the Sun. L2 is just on the opposite side of the Sun. And so it's going to be farther than the Moon. It's going to be about 1 million miles away from Earth, opposite the Sun. And that way the Earth will always block the Sun, and it's going to be a bit of a halo orbit for stability reasons, it can't be right at L2 all the time. And there's a Sunshield. I haven't mentioned the Sunshield. The Sunshield is going to keep the instruments cool, and it is 5 layers, and it is Kevlar, whatever that is. It's nice and cool, and it will keep the primary mirror from being close to the Earth or the sun on the sun side. And so we've got that primary mirror. There's a secondary mirror like all telescopes do. The Sunshield is about the size of a tennis court. And it's going to be unfurled in space. Things that don't need to be kept really cold, like the communication antenna and other things, can be put on the instrument side, on the other side of the Sunshield, but all of the instruments and things that have to be cold need to be kept between the Sunshield and Earth. Webb, the most difficult part of Webb is going to be the unfolding. About 1 month after launch, it's going to start unfolding. And this shows the unfolding sequence. It launches from a rocket, and the Sunshield is going to be deployed, and everything, the mirror will separate and do all these things, and then it will be fully enabled, and it's got to cool down, and science will only start taking place 5 to 6 months after launch. And I have a longer video here from Northrop Grumman, which is about the launch and deployment. And Northrop Grumman is in charge of that.
As the sun rises over the Guiana Space Center, the team conducts final checks on the health and status of the Ariel 5 rocket and its payload. The James Webb Space Telescope, NASA's #1 science priority. The Webb telescope is designed to look back to a time when stars and galaxies were first forming, over 13.5 billion years ago. With its revolutionary design and capabilities, the Webb telescope is about to unleash a new dawn of discovery. Seconds before liftoff, the Ariel 5's liquid-fueled engine comes to full power, followed by the ignition of 2 solid rockets. Liftoff. The Webb telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb's spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload carrying is jettisoned and falls away. Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. Near the end of powered flight, the roll program stops and the launcher then assumes the proper attitude for separation. After separation from the Ariane upper stage, the Webb telescope continues its journey to L2 under its own power, taking the next step to its final orbital station 1 million miles from Earth. The Webb telescope is about to unleash a new dawn of discovery. The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit. And the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirror, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb telescope passes the orbit of the moon. Webb's initial transformation is the deployment of the Sunshield pallets. Tower separating the telescope and instruments from the spacecraft and Sunshield is next. Next, the aft flap deploys. This is key to managing momentum buildup and fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the Sunshield pallets reach their final positions, the membrane launch restraints are released. These have kept the Sunshield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The Sunshield protective covers roll back, permitting membrane deployment. The covers over the core region release next. Then the mid-booms extend and the Sunshield assumes its hexagonal tennis court-sized shape. It is now time to tension the Sunshield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the Sunshield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's at almost 600 degrees. True fire and ice. Once in the shadow of the deployed Sunshield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft portable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission, so that it does not overwhelm the faint infrared signals to be collected from the cosmos. The cord fold wings deploy and latch in place, completing the major deployments of the largest telescope in space. As the Webb telescope continues out to its operational orbit around the Sun-Earth L2, the observatory continues to cool down to its final cryogenic temperature state. A trajectory correction applied 29 days after launch puts the Webb telescope into its halo orbit, a key part of the mission design. The Sun-Earth L2 point is where Webb's orbit around the sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth and all eclipses. Additionally, the sun, Earth, and moon, the brightest objects in the sky, are hidden by the deployed Sunshield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery. Once the mirrors and detectors are sufficiently cold, the wavefront sensing and control operations can begin. This sophisticated multi-step operation's ultimate goal is to position each of the Webb telescope's movable mirrors into their correct final positions and orientations. Once the mirrors are aligned, the mission team will continue checking out the science instruments, preparing them for operation. Commissioning is completed about 160 days after launch. The science mission is ready to begin. This brings to fruition the work of the thousands of members of the Webb team from the United States of America, Canada, and Europe. Astronomers from all over the world can now use this facility to study the universe. NASA's James Webb Space Telescope is a game changer. Discoveries made by this observatory will rewrite textbooks, inspiring the next generation of future engineers and scientists. This revolutionary tool will provide an unprecedented view into the birth of the first stars and galaxies, unleashing a new dawn of discovery.
Okay, and I hope you enjoyed that as much as I did. It makes me very, very excited about Webb and all that it will find out, and all this that it will find out that we don't even know. We don't know yet. How do we talk to Webb? The Deep Space Network has three radio listening devices around the world. The one is in California, there's one in Spain, and there's one in Australia. And no matter where Earth is facing, it can receive signals. So commands to Webb will be relayed from the Space Telescope Science Institute in Baltimore, Maryland, the people who also control Hubble, to the Deep Space Network, and they'll beam them up to Webb. And the things that Webb discovers, its data will go back to the Deep Space Network and will be relayed to the Space Telescope Science Institute, and that will work fine. We've done that with every other mission that is not manned, that anybody does, that we do, or the Japanese, or the Europeans. The Deep Space Network is the kind of go-to, and it was recently upgraded so it can receive even more information. So it relays all the decisions that it wants Webb to make, and all the research, the science that Webb does. The Sunshield technology is this. The Sunshield is very, very thin, 5 thin layers, and they are silicon coated kapton, and you can see that the whole thing is and it's about the size of a tennis court, and it reduces the temperature on the hot side. Somebody figured out it's equivalent to SPF 1 million, if you want to think about it in that way. The Sunshield, it's a very good Sunshield. And in addition to the Sunshield, the mid-infrared instrument also has an active cooler, kind of like a refrigerator, and it's got energy for that for at least 10 years. Now the launch is now slated for December 18th or later. When the Webb people gave me my training, they said, don't plan an event for the launch, because the launch is occurring because at the ESA, at the European facility in French Guiana, that's because closer to the equator somebody is, the faster Earth is already moving, and so the more help the spacecraft has. And because NASA isn't in charge of the launch, our European partners are. If it gets delayed, it's nothing that NASA can control. So right now the spacecraft is in French Guiana, so there's no reason that we know of for it to be delayed. The last delays were because the rocket, the Ariane 5, had some problems, but those have all been fixed now. It will arrive about 1 million miles past the moon at the second Lagrange point, and that will take a little bit of time, and then it has to cool. And we've already seen this particular video, but it shows you what Webb's orbit will look like. It's going to be at L2, pretty much near L2 all the time. You can see here's the moon and Earth, and L2 is about 4 times further from the moon, from Earth as the moon is. Moon is about 250,000 miles. And you can see there's the moon, and there's the other L points, but there's L2 right there, and the James Webb, and what its orbit will look like, a little bit up and down, but always in the shadow of Earth, and not being towards the sun. Now, the Webb in its development has already proven that it's got some science innovations. One of them is that the technology for shaping Webb's mirrors now helps with eye diseases and improved surgery features. The interferometers that were developed for Webb, those pulse lasers, now helps the aerospace industry and semiconductor and medical industries. It has helped Hubble, and the advanced detectors are now the choice in astronomy for looking in the infrared. So it has already proven, I can't really say it's worth because it costs several $billion, but it really has helped. And there's a lot of people behind the Webb, not only NASA, but the European Space Agency and the Canadian Space Agency, Northrop Grumman, the Space Telescope Science Institute, and all these people contribute to Webb. I believe it's 14 different countries and 29 US states have contributed to Webb. So it's takes a team, always takes a team. And if you're a young person interested in a career in NASA, NASA needs everybody. They need scientists, they need engineers, they need people who serve their meals, they need people who engineer their instruments, who clean their instruments. They need artists, they need graphic artists, they need PR people. Whatever you have a passion for, NASA needs. So definitely think about NASA as a possible career. And they've already got quite a few people who have submitted and been accepted for early observations. And this shows the range of the early observations that have been promised. The first galaxies, exoplanets, stars, the assembly of galaxies, galaxies over time, and our own solar system. And this is something that's coming up next. The Ariel mission, which the European Space Agency is launching. It shows a hot Jupiter in front of a star. Ariel is going to look only for exoplanets. They think exoplanets, we all think that the search for how habitable things in the universe might be and our galaxy might be, and possibly life. Just because something is habitable doesn't mean it's inhabited, but they'd like to know if there are habitable planets out there, and even better, there are inhabited planets out there. And we've seen thousands right now. It's amazing. In the last few years, that really has exploded. And this is hot Jupiter in front of its star. Ariel will see it, and Webb will see lots of stars and planets, exoplanets as well. And I think that's it. Yes. Now, finally, I can take a breath and hopefully people have questions. If you have a question, just write it in the chat or speak up if you can.
That was a wonderful presentation, Carol. Thank you. I'm giving everyone a few minutes to see if they need to type any questions into the chat, but you can also unmute yourself and ask.
Well, let me stop sharing so I can see all your names.
If we don't have any questions, I just want to say thank you again to Carol for taking time out of your busy day to talk with us, and it kind of gives us a breakdown of the Webb telescope. I was really fascinated with it, and I didn't know a whole lot about it, so it was really interesting to learn everything.
You know, it's not just a replacement for Hubble, it's a true extension. And originally I was kind of disappointed. What? No pretty pictures, it's not going to be invisible. But you know, the infrared really talks about things from long ago and far away.
Just a reminder, everyone, we had some people join late. I have been recording this session and we will post it to our YouTube channel, but I will send out a link either tonight or first thing in the morning, so you can rewatch if you came in late and catch what you missed. So at this point, I think we can go ahead. Oh, we do have a question from Ben and Tiffany. How many years does it take for a star to die? And if someone is interested in being part of NASA, what is the first step?
Okay, it depends on the mass of the star. Actually, the more mass it has, the faster it uses its fuel. So stars that are very big and massive, they only last a few million years. The sun is going to last about 9 billion years, billion with a B. It's about halfway through, about 4.5 billion years through its cycle. And the universe is only 13.5 billion years old. And we think that there are stars that are even older than our universe. I don't know how that can be. No one knows, but really small stars last for more years than it would be the universe. And how can someone be involved in NASA? Well, there's, like I said, whatever you're talented in, but usually they require a college degree of some sort. So get a 4-year degree in, if at all possible, in some field, whatever field you're passionate about, and or they probably won't consider you.
All right, thank you. So at this point, we're going to end the session. Thank you to everyone who attended, and you'll get an email from me in a little bit with the recording. Okay. Y'all have a great afternoon.
Could you put my email
yes.
on your information? Because I forgot to put it on the slide in case anybody has any questions they'd like to email me.
That would not a problem at all.
Thank you.
Thanks so much, guys. Y'all have a great afternoon. Thank you again, Carol.
Thank you.